In this video, we're going to look at Green's theorem. And Green's theorem relates a line integral around a closed curve to a double integral over the area inside that curve. So, for example, let's say you have this closed curve going around this boundary here. Again, it's specifically a closed simple curve. Remember, the simple curve means the curve isn't going to cross over itself, and it has to be closed. It has to start and end at the same point. So we have a closed curve here, and suppose we want a line integral over that curve. Instead of doing that, we can do this double integral over, sometimes they call this R, or sometimes you can call it D for like your domain. Either way is fine. I called it here D, but if you see R, it means the same thing. And to do the Green's theorem, you have to take the derivative of Q with respect to X and subtract the derivative of P with respect to Y. And then you can apply Green's theorem. And a couple of things are important. As I said, C must be a closed simple curve. And also, the first partial derivatives must exist. And be continuous on the domain. So these are required in order to use Green's theorem. We have to have a closed curve, and the first partial derivatives, that'll be the derivatives of P and Q with respect to X and Y, must exist, and they must be continuous over the whole domain. Another thing to mention here, Green's theorem is based on positive orientation. So, and that means that if you're going around this curve, let's say you are standing along the curve and walking in the direction of the arrows, the domain would always be to your left. So like here, for example, suppose you're walking along the curve here, the domain will always be to your left. And then Green's theorem is set up for that case. Now, if it's the other direction, let's say if you're walking along the curve and the domain is to your right, that's called negative orientation. In that case, you would have to change this to a negative when you do the integral. So if your original curve was, in this case, clockwise, then you would have to put a negative over here. But if it's counterclockwise, like it is here, that's positive orientation, you just keep it positive like it is here. Another important thing to remember is notation. So like we are given something like this. So this notation here, sometimes it could be written this way, like f, let's say, is a function of x and y. This could be written as pq, like this. And the dx dy could be written as dr. like this. So this up here could be written as a dot product with F and dr. So for example, you could write Green's theorem this way. F, and sometimes you leave out the X, Y, because that's just notation. Sometimes you put it in, it's up to you. Dot dr. This then is the same as what we have up here. And so that's would be another way we could express Green's theorem. Like this. So Green's theorem could be expressed this way. Or it could be expressed the way we had it originally up here. And the other thing to note is that Green's theorem is a theorem for two dimensions. You know, we just have two dimensions, like say x and y are independent variables, and this surface is in two dimensions. Now you could apply it, say, instead of in the xy plane, you could apply it maybe say the xz plane or the yz plane, etc. But it is in two dimensions. Here, in general, we can kind of think of it as always being in two dimensions. And it will always be in two dimensions. Green's theorem will always be in two dimensions. But it could be, as I mentioned, xz or yz, but usually we'll be doing it just in xy plane. And so those are the theorems in this form or this form. Just keep in mind that these two mean the same thing because the vector field can be expressed as PQ and dr is dx dy. Next, let's take a look at this problem. We're asked to evaluate this line integral over the curve C, where C is the boundary of the triangle with vertices 0, 0, 0, 2, 2, 2, and we're told it's positively oriented. Now, if we were to do the line integral directly, it would get really, really messy because look how bad these functions are. So we'll try Green's theorem. And so let's take a look at that. So remember, for Green's theorem, this line integral is going to be equivalent to the double integral over the domain inside of our curve. So let's maybe we can take a look at what curve we have. And we're told the vertices are at 0, 0, 0 on the x, 2 on the y. And then 2 on the x, 2 on the y. And so again, 0, 0, then we have like 0, 2, then 2, 2, and then it goes back to 0, 0. Looks like our curve looks something like this. And so we're told that we're positively oriented, so our region that we're enclosing is in here, so that must mean we're going this direction with our C. And so let's take a look at this. So as I said, first of all, we're going to need to do dq dx. So we have to identify q. So q is whatever is with dy, which multiplied by dy, that's this over here. And we're going to need to do dq dx. So let's do that. dq dx. Now that has just y's, that's going to go away. This has y's, that's going to go away. And this is going to be, looks like it'll be negative y, like this. Because this is going to be 0 with respect to x. This is 0. And this with respect to x, is keeping everything else constant, just going to leave us negative y. So let's do dp dy. That's the other piece that we need. And so again, look over here. Whatever's multiplied by dx will be your p. Take the derivative to that with respect to y. This is going to go away. This is going to go away. This is going to go away. And so it looks like we just have 2y. So now our Green's theorem says, and I won't rewrite this big equation up here, but I'll sort of just write the symbols. It says p dx plus q dy over curve C is going to be equal to the double integral of dq dx minus dp dy dA. And in our case, we found that dq dx was minus y and minus 2y, like this. And now we're going to do the double integral over this domain that was enclosed in our curve. So we're going to do it over this here. So we're going to need some equations of these lines. Of course, here, the equation of this line right here will be, it starts at 0, so its y-intercept is 0. And it looks like the slope is like 2 up and 2 over 2 over 2, or 1. So y is equal to x is going to be the equation of this line. And let's say if we integrate with respect to y first, we'll remember when you do these double integrals, put some lines in the positive direction of the coordinate you want to integrate first. So if we put positive arrows in the direction of y, our arrows start at here at y equal x, and they end at this line over here. What's that line? Y equal 2. And then think of how your region projects onto the x-axis to get your last bound, and it goes from 0 to 2. Like this. So, of course, always remember that if you're doing y first, put arrows in a positive y direction. Wherever the arrows start is your lower bound. They start on the function y equal x. Where the arrows end, your upper bound, y equal 2. Then see what projects on the xy plane, 0 to 2. And that's our dy and dx. And so let's integrate this. Let me just so this is going to be minus 3y. Let me bring the minus 3 in front. And this will be just y, be our integrand, dy dx. So integrate that, and we have still have our negative 3 in front. Integrate with respect to y. That'll give us y squared over 2 from y equal x to y equal 2, x equals 0, x equal 2, dx. And put these in. That'll be 2 squared over 2. Then put our lower bound in, minus x squared over 2 dx. So I just put the upper and lower bound in. And so this is going to, that'll end up being 4 divided by 2, which will be 2. And then so let's integrate with respect to x. So as I mentioned, this is going to be 2 here. And we integrate with respect to x, that'll give us 2x. So the 2 will be 2x. And then this will be minus x cubed divided by 6. Because we'll multiply by 3. And then evaluate it from x equals 0 to x equal 2 like this. Then put the bounds in. Minus 3, 2, 2, minus 2 cubed divided by 6. That'd be the upper bound minus 3, 0, minus 0 like this. That'll be 0, minus 3, 4, minus 8, 6. And so if we simplify this, this is going to be 4/3, and this is going to be what, 12 thirds and 4/3 here. So that'd be 8/3. And the 3's cancel. And the answer is minus 8. So once again, Green's theorem, instead of doing the line integral around the curve, you do the double integral over the area inside the curve and do that, and we get our answer. And notice what's very important about Green's theorem is that it tremendously simplified the integrand. Look how bad the integrand was here before we started. We took the q dx, the p dy. It simplified all that to negative 3y. Now, there are going to be some cases where it doesn't simplify the integrand too much, and or the domain for the double integral it could be bad. In that case, you probably don't want to use Green's theorem. But if it does simplify the integrand and makes nice bounds on your double integral, then that's the time when you want to apply Green's theorem. Next, let's take a look at this example here. We're asked to, once again, asked to evaluate this line integral. And the curve C is positively oriented boundary of the circle x squared plus y squared is 16. So again, we're going to use Green's. And just drawing our domain here, our circle would look something like that. So we have a circle of radius 4. And again, you can see this is x squared plus y squared, 4 squared, so radius 4. And we're told it's positively oriented, so it'll go like this. We really didn't even have to draw the orientation since we were told it was positively oriented, but that would imply it's going counterclockwise. Again, the domain would always be to your left. And so let's do Green's theorem. Once again, we're going to need dq dx. And of course, this is q. So if we do dq dx, that will be 6x squared. And over here, it's going to be 0. So that got rid of that part of q there. Then we need to do dp dy. This is p, whatever is multiplied by the x is p. So dp dy. And this is going to be also minus 6y squared. This has no y's in it. That'll go away. So we just have that. So no, we're going to apply Green's theorem. Just keep in mind what we have, p dx plus q dy. And you could have written this down here, but it's too long, so I just wrote the symbols here. This was p, this was q, and we say that that's equal to the double integral over the domain. In this case, the domain is inside here of dq dx minus dp dy dA. And then over here, this is going to be 6x squared minus 6y squared. And keep in mind what we're going to have. We're going to be doing this. I'll sort of note here. We're going to end up doing this over this circle. Circle of radius 4 centered at the origin. And let me just put dA in here for right now. And then if we factor out, so we're going to end up with 6x squared plus 6y squared. So let's factor out the 6. And we have x squared plus y squared dA. Once again, circle of radius 4. And finally, this is really calling for polar coordinates because we're integrating over a circle and we have this x squared plus y squared. So let's change the polar. Just put a note here. And have our 6 in front. And then remember, for polar, x squared plus y squared is r squared. And always remember the Jacobian. When you change the polar, be sure to put your r and then dr d theta. You always have to multiply that extra r whenever you're changing the polar from Cartesian. And then we want to integrate over this circle, and that's going to be from r equals 0 to r equal 4. And then, of course, the circle goes all the way around. Theta is 0 to 2 pi. And I'm putting a lot of extra steps just so everyone can see what's going on. But when you would do this on your own, you can skip many of these steps. For example, you can skip these steps or right in this with the circle. Is you could probably just, once you see what's happening here, you could probably just jump right to polar. And the same thing here. You could have probably just done the, recognize this was r cubed, then just done the integral right there. So let's integrate this. So we integrate that, that'll be r to the 4th over 4. R equals 0 to r equals 4. D theta. 6 theta 0 2 pi. We put a 4 in here. And when we put a 4 in here, one of the 4s is going to divide. So instead of being 4 to the 4th, we'll make it 4 cubed. And then the lower bound is 0. And then integrate again with respect to theta. And we put those in. 4 cubed 2 pi, like this. And when we multiply this out, we get 768 pi, like that. Next, let's take a look at this problem here. We're asked to do this line integral. And again, don't let this throw you off. Remember, this is the same form we had previously. We said that p dx plus q dy was the same as having the vector field dotted with dr. And that's what we have here. And so we're given this vector field. And so when we actually do this in a minute, this will be P, this will be Q. And now the curve C is positively, or the positively oriented boundary. of the region between the line y equal 2x and the parabola y equal x squared. And so let's actually draw this to see what region we're talking about. So let me draw the line. So again, the line has a slope of 2. So it's 2 up over 1, 2 up over 1. So this is going to be the line y equal 2x. And of course, the parabola will go up like that. And notice that they intersect at x equal 2, y equal 4. And if you weren't sure that, you could set these two equations equal to each other. 2x equal x squared. We want to find the intersection point. So we want to find where this is equal to that. These are both equal to y, so we can set them equal to each other. Now we know one point is going to be at x equals 0. Let's actually factor this. This is kind of the most precise way to do this. So we factor this. Notice the things that make this 0 is x equals 0, which obviously the starting point, the intersect the starting point, and then x equal 2 will make this 0. And so at x equal 2, y will be 4. And that'll be, you can find that from either equation. X is 2, y is 4. So they're going to intersect at this point right here. 2, 4. And so now we're going to do Green's theorem. And so once again, we're going to need derivative of q with respect to x. Which again, that's going to be 0. And this is going to be what? 4x cubed. And dp dy, derivative of this, that's going to be 4x cubed. 4x cubed. And this is going to be 0. This is going to be 0. This is going to be 0 because there's no y's in either of these. Now let's set up our double integral. So again, we said before that if we have f dot dr over curve, we have the double integral over the domain or the region of dq dx minus dp dy dA in our case. And I'm going to set up the bounds even though it's going to turn out we're not going to need them. So dq dx is 4x cubed minus 4x cubed. And now let's put our bounds here. So let's say we're integrating over this region so that you can see the region is going to be in here. And this was our parabola. And so if we were to start with the y direction, we would integrate. If we put arrows in the positive y direction, they start at y equal x squared. And they end at the line y equal 2x. And then you can think of how that area projects down onto the xy excuse me, onto the x-axis. And so x, the region is covered from 0 to 2. You can see x covers the region from 0 to 2. And dy dx. So that's what we would normally do. Now, one of the things, though, we notice right here, that's going to be, this is 0. So that'll be just 0. Now, normally, 0 could have come from a constant. So if you were to integrate it, you would normally get a constant. But if you have bounds, remember any constants will cancel out. So whenever your integrand is 0 and you have bounds, the final answer is going to be 0. And again, as I mentioned, if you didn't have bounds, when you integrate it once, you would get like a constant c when you integrate with respect to y. And then you integrate with respect to x, you would get like, say, a cx plus another c, but we have bounds. So again, whenever our integrand is 0 and you have bounds, your answer will be 0. Next, let's take a look at this problem. Once again, we're asked to evaluate this line integral, where C is the positively oriented boundary of a triangle with vertices 0, 0, 2, 5, and 6, 0. So let's take a look at this. Let's maybe draw this. And one of the vertices is at 0, 0. The other one is 2 in the x, 5 on the y. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6 on the x and 0 on the y. So it looks like we have a triangle. Again, 0, 0, 2, 5, 6, 0. Looks like we have a triangle something like this. So again, it's positively oriented. And let me put some numbers here. This is 5. 1, 2, 3, 4, 5, 6. Like this. So since it's positively oriented, C must be going counterclockwise. And once again, we're going to use Green's theorem. So again, let's do our normal stuff, dq dx. Remember, this is q over here. So it looks like the derivative of that is just 1, because this will be 0 when we take the derivative with respect to x. And then dp dy looks like that's just going to be 5. So again, let's apply Green's theorem. Once again, you don't have to write this down every time, just kind of writing it down to help us remember it. And again, you remember your domain is like in here, this region here of dq dx minus dp dy like this. And this is going to be wonder what we have up here. dq was minus 1, excuse me, 1. And then dp dx was 5. It's going to be 1 minus 5 over our domain. And that's going to be minus 4 dA. So now at this point here, we could set up bounds, with respect to x and y and integrate over these. Probably the easiest way would be to do x first in this direction, like say going in the x direction first. And then this would be your lower bound, upper bound, etc. But one thing important to remember here is we have a double integral and there's no variables here. We just had this constant which we could factor out. So whenever you're doing down to a double integral dA, and you know what the area is or can calculate the area easily, then you don't have to do the integral. Now, if the area was hard to calculate, we might still have to go through the integration. But here, we can calculate pretty easily. So again, whenever you can reduce down to just have a dA here or have dx, dy, dx, this is just the area of the domain. And so in our case, we can find the area of these triangles. So like if we look at this here, we could probably break this up into a couple different triangles, do this pretty easily. There are other ways to do this, but I'm going to do it this way. So this first triangle here, the base is 2 and the height is 5. So 1/2 base times the height. And then for this little triangle over here, the base is going to be 6 minus 2, which is 4. And the height is also 5. And so it looks like we have 5, because this will be 1 times 5, 5. This will be 2 times 5, which is 10. So that's 5 plus 10 is 15. And if we multiply that by -4, we get -60. So again, always remember that if you get down to this point here and you know the area of the domain or can easily find it, that's all you need to do. So here in this case, we just calculated the area of the domain here. There were two triangles added together and got our answer. And again, if it's a complicated domain, you might have to set up the integral anyway and do it. But in this case, we didn't have to do that. But remember, you can only do this if there are no variables here at all. And you have factored out all the constants. So factor out all the constants, and then there could be no variables in your integrand. If that's the case, then you can just find the area of the domain.